Let's study about real and apparent depth. Now, children, if an object and observer are situated in different medium, then due to refraction, an object appears to be displaced from its actual position. Like when you stand near a swimming pool, then you find that the bottom is not so deep as you actually get to know when you enter the swimming pool. So remember that you are that an object and observer are situated in different medium, then the object appears to be displaced from its actual position because of the phenomenon of refraction. Now here you can see a person standing at the side of a pool, and the bottom you can see there is a block which will appear to be him at this particular position. This is the object at the bottom of the surface, and this appears to be at here. So actually the this what is shown is the actual depth of this block, but the person seems this block to be over here. So this becomes the apparent depth of the object. So, real depth is the actual distance of an object beneath the surface, as would be measured by submerging a perfect ruler along with it. Or you can say in this case, the real depth will be the actual distance without the water. Apparent depth in a medium is the depth of an object in a denser medium as seen from the rarer medium. Its value is smaller than the real depth. In this case, we are considering the situation when the object is in the denser medium. So light will be moving from the denser medium to the rarer medium. Now here, this is a diagram which you are already well aware of. So you can see that there is an object O. We have taken a point O. One ray has been taken falling normally on the surface, and you all know that it will go undeviated. Another ray is taken to be falling obliquely on the surface. It is touching this point B. From here, this n dash is the normal, and since it is traveling from water to air, so it bends away from normal. Now, this is the incident ray, this is the normal, so this is the angle of incidence, and this is the refracted ray, this will be the angle of refraction. Now, to a person who's observing from here, to him, this point O will appear at this point I. This we have obtained by extending this back. It will meet this ray OA at this point I. So, the real depth of this is AO, whereas the apparent depth, the depth that appears to be the observer is AI. Fine. Now, children, if you apply geometry over here, then see this OA and N dash will be parallel to each other. So, will be the transversal. So this is I, this will also be I. I hope you know that this will be alternate angles. Similarly, if you consider IC as the transversal, then this will be angle R. This will be which angles? Corresponding angles. Now, we will just redo this is we are considering a ray OA which is incident normally on the surface. Now this will pass straight. You know a ray which falls normally on the surface travels undeviated. So this ray has gone straight. Then we have considered another ray from O, right, the object, and it is incident at an angle I along OB. This ray gets refracted and passes along BC. On producing this ray BC backwards, it meets at I and it appears to come from the point I. So, AI represents the apparent depth. We have already done this. This is just a revision. AI represents the apparent depth, which is less than the real depth AO. Now, this ray OA had fallen normally on the glass slab, and BN, this NN dash is a normal. These both are perpendicular to the surface, so are parallel. And OB is the transversal. So when we use your geometry, then angle AOB will be equal to angle OBN. These are alternate angles. And if you see these angles, angle BIA and angle CBN, these are the corresponding angles. So children, in triangle BAO, triangle this one BAO, sine I is equal to BA upon OB. You know sine is given by perpendicular upon hypotenuse. So perpendicular is AB and hypotenuse is OB. Similarly, if you consider the triangle IAB, IAB. Again, over here, this is R. So here, sine R is equal to, again, perpendicular, which happens to be BA upon hypotenuse is upon IB. Okay, children, we know that light is traveling from water to air. So you can write W mu A. That means refractive index of air with respect to water is sine I upon sine R. In just few seconds before, we have found the value of sine I. I hope you can recall that sine I we had found to be BA upon OB, and we had found sine R equivalent to BA upon IB. Let's substitute these values. So you get sine I BA upon OB, and you know when you divide it will become multiplication. So I'll have IB upon BA. So here BA and BA will get eliminated and you have IB upon OB. So basically what you have got is that refractive index of air with respect to water is coming out to be IB upon OB. But what is IB and OB? IB is this distance, isn't it? And OB is this distance. Now see, what is this? This is B is the point of incidence. This point of incidence could have been anywhere. So to get a concrete result, we make an assumption over here that point B is very close to A, or you can say that we are viewing nearly vertically upwards. So over here, I'll replace B by A in both cases. So I'll have IB equal to IA. Similarly, I'll have OB equal to OA. Therefore, you can say that W mu A is equal to IA upon OA. Now, children, what is IA? IA is this distance, isn't it? So, this is apparent depth. So, here we write W mu A is apparent depth upon the real depth. And if you use your principle of reversibility, you can also say A mu W is equal to real depth upon apparent depth. So now you can see that refractive index is also found in terms of not only the sin I upon sin R or velocity of light or using wavelength. We also have refractive index in terms of apparent depth and real depth. So refractive index of the denser medium with respect to the rarer medium will be equal to real depth upon apparent depth. So it can be concluded that refractive index of denser medium with respect to rarer medium is given by A mu m equal to OA upon IA, that is real depth upon apparent. Now children, just now we have seen that refractive index is given by the relation real depth upon apparent depth. Now I have changed the subject over here. That means I have found apparent depth. Apparent depth is coming out to be real depth upon refractive index. So we have put a symbol T for the real depth. Refractive index of course is given by mu. So apparent depth is obtained simply by interchanging these two places. So apparent depth is equal to real depth upon mu. Now if you wish to find out by how much is the object being raised, so I can say that if I want to find out by how much the object has shifted, then I appears to be shifted. I'll find real depth minus apparent depth. When I subtract the real depth and apparent depth, then I will get the apparent shift of the object. So here apparent shift will be real depth minus apparent depth, that is T, which is the actual depth, minus T upon mu. Here we have found the apparent depth. So it is simply taking T common and you get 1 minus 1 upon mu. So finally we see that the apparent shift in the uh, position of the object is given by the relationship T into 1 minus 1 upon mu, and it is involving two things, thickness and the refractive index. So apparent shift, this formula is just for your recall. So apparent shift is equivalent to T into 1 minus 1 upon mu. Now considering the above relation between the shift in height, thickness of the denser medium and refractive index, you can very well conclude that the shift by which an object appears to be raised depends on, first, the thickness of the denser medium. Second, refractive index of the denser medium. Now, this also shows that if the refractive index of the medium is more, then the apparent shift will be less. So, refractive index of medium is more for violet light and less for red light. So, the shift is more for violet light and less for red light. So if a slab is placed over a colored matter, then different colors appear to be raised differently. You can see in the diagram that the word Vibgyor, that is only written to represent the different colors, and you will find a glass slab placed over it, and you will find that the rays of the violet color is much larger than the rays of the red color. So this deals with the apparent and the real depth with respect to the refractive index. Now, time for doing some numericals. So we can do some numericals. Get ready with your copy. So the first numerical is a fish at the bottom of a pond appears to be 1.2 meter from the water surface. What is the depth of the pond? Start doing. and soon you will get the solution for it. So now see your formula for refractive index mu is equal to real depth upon apparent depth. So here the refractive index is given to be 1.33. So we have written 1.3 is equal to real depth. That is what we needed to find. What is the depth of the pond? That is the real depth. Upon it appears to be 1.2 meter from the water surface. So apparent depth is 1.2. So real depth will be equal to 1.33 into 1.2. That gives us 1.6 meter. So the depth of the pond is 1.6 meter. I hope you got it right. Now let's move to the next numerical. The next numerical is an object at the bottom of a beaker filled with a liquid up to height of 10 centimeter. If the refractive index of liquid with respect to air is 4 by 3, find the apparent depth of the object. Start doing. Well, I hope you must have done. Now, the it is given, it is filled up to the height of 10 centimeters. So this 10 centimeters is the real depth. So real depth is 10 centimeter. Then it is given a mu w is 4 by 3. So here a mu w is equal to 4 by 3. Now refractive index is equivalent to real depth upon apparent depth. So I get 4 by 3 is equal to 10 upon apparent depth, or apparent depth will be 10 into 3 by 4 equivalent to 30.4, that is 7.5 centimeter. So the apparent depth will be 7.5 centimeter. The next numerical, a glass block 3 centimeter thick is placed over a stamp. Calculate the height through which the image of the stamp is raised. The refractive index of glass is 1.54. Well, let's see how to solve it. Now here again, first the formula A mu G will be real depth upon apparent depth. The refractive index of glass is 1.54, therefore 1.54 is equal to, glass block is 3 centimeter thick, so that means the real depth is 3 centimeter, is equal to 3 upon apparent depth. So apparent depth will be equal to 3 upon 1.54 equal to 1.94 centimeter. The height through which image is raised is 3 minus 1.94 equal to 1.06 centimeter. Children, you could have even done this numerical directly by using T into 1 minus 1 upon mu. This can also be done. The next numerical is a postage stamp placed under a glass appears raised by 8 millimeter. If refractive index of glass is 1.5, calculate the actual thickness of the glass slab. Now, we'll assume the thickness of the glass to be x. Then the apparent thickness will be obviously x minus 8, because here they have given that it appears to be raised by 8 millimeter. That means they have given the apparent shift to us. So now if you recall, mu is equal to real depth upon apparent depth, or you will get Mu, put the value, it will be 1.5, right? Real depth we have assumed to be x. So you have 1.5 is equal to x upon apparent depth. Apparent depth will be x minus 8, right? Now cross multiply 1.5x minus 1.5 into 8 will be 12, will be equal to x. So 1.5x minus x is equal to 12, or x is equal to 12 upon 0.5. This is giving you x is equal to 60 millimeter. So the actual thickness of the glass is 60 millimeter.